So in the next 30 to 40 minutes, I would like to share whatever little bit I know about the mechanical behavior of materials. Okay. And I believe that mechanical behavior of materials, if we are able to understand, then it gives you an insight as to the pathway to failure analysis. As I already mentioned, every mechanical test is a destructive test leading to fracture. And then we try to understand it in terms of deformation and damage. So what is failure? All of us know we had in life itself so many failures. And as Dr. Isha Prasad said, failure is an essential requirement to make a success. So when a part or a device, the definition of failure, the textbook definition is that when a part or a device can no longer perform its intended function, we declare the part as failed. That is the textbook definition of failure. And then what are the fundamental causes of failure of systems and components? Of course, we are talking in the metallurgical context. So the fundamental causes of failure are, one is a deficiency in the design. That means the design was not proper. Or we have operated the component beyond the design conditions, maybe in terms of higher temperature of operation or overloading or whatever. So we have operated beyond the design conditions. Or there has been a deficiency in the selection of materials. We did not have the correct property of the material, or we overestimated the properties of the material. We made a wrong choice of the type and grade of material. So these are the three major, causes for failure: deficiency in design, operation beyond the design conditions, and deficiencies in the selection of materials. But there are other reasons too. One is the mechanical property of materials, because when we are designing a component, we should have the data on mechanical properties of the material at the relevant condition on the table. So if we have the right information, then we are in a good stage. Some of the other causes of failure are imperfections in the material. When I say imperfections, there can be some laminations or cavities, okay? Or there can be microstructural stability, because when we talk about engineering systems, we are talking of alloy systems, and alloys can undergo a lot of microstructural change as a function of temperature and time. And when the structure changes, the properties also change. Yet another cause can be deficiencies in processing. When we make, different product forms like plates, there can be again laminations or, a lot of inclusions, or we have to make components by welding, and always welds are considered to be weak links. And finally, environmental effects. We might have designed or chosen design data based on one particular environment, and the system may be operating in a different kind of environment. So these are some of the fundamental causes of failure of a metallurgical system. So now we come to the second definition, and that is about the definition of failure analysis. It can be defined as a systematic, evidence-based, science-based, and data-driven approach that is employed for investigation of failures occurring during service. As I mentioned, I am not an expert on failure analysis, and I'm sure that we will learn a lot on failure analysis when we listen to the talk by Dr. Narayan Murthy and Dr. very well-known specialists in this area. So what are the various stages of failure analysis? First, we should get the background data. Then we have to carry out a set of preliminary examinations. We should collect samples and evidences, should carry out some chemical analysis, non-destructive tests, and then destructive mechanical tests to determine the material property, that is the property of the service exposed material or the failed material. And that is normally followed by macroscopic examination, microscopic studies, metallography studies, failure mode analysis, fracture mechanics analysis, and finally, of course, the report and recommendations. So during this failure analysis, we are initially looking for signatures of failure. And then we have to apply our mind, do a lot of analysis, check with the data, properties of the material before entering into service, and then we have to make an informed decision about, informed understanding about the cause of failure analysis. Now coming back to the core of my topic, and that is on mechanical properties of materials. We know that the property of a material depends upon how it responds to a kind of loading. And depending upon that, we have tensile properties, fatigue properties, creep properties, creep fatigue properties, and impact properties. All these represent the response of a material under different type of loading. And of course, these properties change with temperature, change with environment, change with the microstructure, and as I said, change with the wells. So failure analysis can start by understanding the deformation behavior of the material, because the deformation leads to damage in the material. And if you are able to understand the formation and evolution of damage, then we can get a better grip of failure, and you will be able to see a lot of signatures during your failure analysis program. The textbook list on mechanical properties of materials, all of us know, are hardness, which is normally determined at room temperature in most cases. Tensile properties, both at room temperature and higher temperature, and even at sub-zero temperatures. Impact properties, which are basically low temperature property of the material. Creep is essentially a high temperature property, and fatigue is a property that is important both at room temperature and at high temperature. And as I said, all these properties vary as a function of temperature, as a function of rate of loading and nature of loading. Like for example, impact, it measures the resistance of a material to a very sudden loading, very rapid rate of loading. Okay. So that is what an impact is, very high rate of loading. Whereas at the tensile properties like yield strength or the tensile strength, the ultimate tensile strength, they represent the behavior of the material, how it resists moderate rate of loading, maybe 10 to the power of -3 to 10 to the power of -5 per second. So medium rate of loading, how the material responds, is decided from tensile properties. When you talk about creep, creep is the behavior of a material at constant load. In impact, it is high rate of loading. In tensile, it is medium rate of loading. And in creep, it is a constant loading. The load is kept constant. But since the material is loaded at high temperature and is in service for a very long time, it ends up in failure. Material ends up in failure. And then we have the fatigue, where we measure the resistance to cyclic loading. It is no more monotonic loading. It is cyclic loading. You are loading it through tensile and compressive cycles. And then we know that the material will undergo fracture or failure after several number of fatigue cycles. So I will come to damage a little later, but let me now look at fracture. Okay. When we talk about the fracture, it always starts with the nucleation of a crack. And then the crack grows and it propagates. In the initial stage, it will propagate in a stable manner, but subsequently it will start propagating in an unstable manner. And that is when it ends up in fracture. And depending upon the ability of a material to undergo plastic deformation before fracture. See, always plastic deformation precedes fracture, except maybe in the case of impact loading where there is hardly any scope for plastic deformation. But otherwise, in the case of all other modes of loading, be it tensile, be it creep, or be it impact, there's a lot of plastic deformation that happens before fracture. And therefore, there is damage formation between the stage of plastic deformation and fracture. So the fracture can be broadly classified into two modes. One is the ductile fracture, where the plastic deformation is very extensive. And when the plastic deformation is extensive, the crack is stable. The crack is able to resist the further growth of itself, okay, unless you increase the applied stress. And the other kind of fracture is brittle fracture. Brittle fracture means hardly any plastic deformation. It is an abrupt separation of the material into two parts, and there is hardly any deformation, and the crack propagates in almost no time. So crack is unstable, it propagates rapidly with no further increase in the applied external stress. So between these two, ductile fracture and brittle fracture, a designer, a metallurgist always prefers ductile fracture if one has to design for such a failure mode. Now coming back to the tensile curve, all of us, and since there are the majority of the audience is students, that is why I'm going to, little bit to the basics. So all of us are familiar with the tensile test and the tensile curve, which is nothing but we plot strain on the x-axis and stress on the y-axis. And this is a schematic, but it's a typical curve where initially material deforms elastically, it reaches the elastic limit. Then it undergoes deformation, plastic deformation, reaches the tensile strength or the ultimate strength, and thereafter the load comes down due to necking and it ends up in fracture. And then by analyzing the region between the yield stress and UTS, we are able to understand the plastic flow behavior of the material, evaluate analyze the work hardening characteristics of the material. And there are several forms of constitutive equations which relate the true stress and true plastic strain, like the Holloman equations, Ludwig equation, etc., etc. I'm not going to, but basically, these are all relationship between true stress and true plastic strain. And that is derived from analyzing the region between the yield stress as the UTS. Now coming back to the fracture, in the case of tensile fracture, okay, the tensile fracture begins with necking. Necking starts once the deformation crosses the UTS, right? So once it crosses UTS marks the beginning of necking. And as the neck grows, the deformation gets localized in the neck region. That's why the stress is coming down in an engineering stress strain curve. So in the neck, small cavities start forming, okay? And mostly these are associated with, inclusions in the material. No engineering material is free of inclusions. In fact, if you want to, manufacture inclusion-free material, it becomes very, very expensive. You need to go through so many processes, and many times it is not worth the money that we need to pay. Therefore, inclusions are one of the major sources of cavity formation in a tensile deformation. So these small cavities which form, they will start linking, they will grow, and then they start joining or linking, and then they form a crack, okay? And then this crack grows under the action of the applied stress. And a stage will come that the remaining ligament of the material is carrying too much load that it is no more able to sustain and is beyond the fracture stress, and the material separates into two parts. So the tensile fracture always begins with a damage which is inside, internal damage. And it has got at least 4 or 5 stages. Begins with necking, and then the cavity forms, the cavity starts coalescing to form a crack, then the crack grows, propagates, and ends up in fracture. So a macroscopic view of a sample which has been tensile tested is shown here. It is typically called cup and cone fracture. Why is it called cup and cone? See, one part looks like a cup and the other part looks like a cone, at low magnification. This is a typical ductile failure in tension. Now, if you take this fracture, if you examine the fracture surface under a scanning electron microscope, then you will find a large number of dimples, and each of these dimples will be associated with certain number of inclusions. So this is the macroscopic view of a tensile ductile fracture, and this is the microscopic view of a tensile ductile fracture. Now, the other side of the spectrum is the brittle fracture, where there is hardly any ductility. That means hardly any movement of dislocations. So no plastic deformation, and the crack propagates very fast into almost 2 pieces. And the fracture surface will be nearly perpendicular to each other. That means you end up in a flat face. And this happens because the crack is it's a cleavage failure. Cleavage failure occurs when The crack propagates by breaking the atomic bonds along specific crystallographic planes called cleavage planes. So this is the case of brittle fracture in a material. So these are all, very important signatures of failure analysis. Are you seeing a very brittle fracture, or are you seeing a very ductile fracture like the cup and core? Then you can say that, okay, there must have been a very case of a tensile failure in the material. And I would also like to give you a little bit of glimpse about the design aspect, because I'm a little bit familiar about the American Society for Mechanical Engineers boiler and pressure vessel codes. These are the codes which are used in the design of nuclear components. Nuclear components, the design demands a lot of safety. Okay. Now it uses different properties depending upon the performance of the depending upon the operating conditions of the component. So as per ASME, when you are looking at the tensile properties, it says that the stress you can use, the allowable stress, is equal to 1/3 of the UTS, or the tensile strength, or 2/3 of the yield strength of the material, whichever is lower. So you are not using the absolute value of the tensile strength. You are applying a factor of 3. So the safety factor is 3. You are not using the absolute value of yield strength. You are applying a factor of 2/3 on that. That means safety factor is 1.5. And then whichever is lower of this, that will be deciding your allowable stress under tensile deformation. So if you look at this sketch here, okay, so 1/3, you see here that this is where you have the 2/3 of yield strength, and this is the 1/3 of the tensile strength. So 1/3 tensile strength is lower than 2/3 of yield strength. So that means that the allowable stress is given by 2/3 of the yield strength of the material. Now coming to impact. Impact represents the response of a material to very high rate of loading. And an impact test is, or the impact behavior of a material, is normally represented by the impact curve, which is nothing but a curve between energy absorbed in an impact test versus the temperature of testing. So you have basically two regions. You have what is called the upper shelf region, that is the region of very high energy, and that is normally at a higher temperature. And then as you decrease the temperature, you find that the amount of energy absorbed during impact test drops drastically. It comes down drastically, and then it remains almost constant. So that represents the lower shelf energy, and that is at the lower temperature. And you don't want the material to operate in the temperature range where you have very low energy that can be absorbed, that is in the lower shelf region. Okay. And a fracture can be transgranular or it can be intergranular. Transgranular fracture means the fracture is across the grain. So a brittle fracture itself can be transgranular or intergranular. So when we say brittle fracture is transgranular, that means the fracture cracks pass through the grain, and the fracture surface will have faceted texture. Okay, and that is due to the cleavage of crystallographic planes in the grain, and the crack will propagate very fast along these crystallographic planes. So that is what is shown schematically here. The red line shows a crack passing across the grains. And then you have the intergranular fracture, that is the crack is propagating along the grain boundaries. There also it's a grain boundary phenomenon. So the grain phenomenon is not much. It is the grain which gives you the deformation and the plasticity and the elongation. Since there is hardly any activity in the grains, the whole operation is along the grain boundary. Again, we will have very little ductility. So this shows, if you look in the SCM, an impact test sample, you may see either a case of transgranular fracture, or you may see a case of intergranular fracture, where the crack is propagated along the grain boundaries. So you can see each of these grains very clearly and its faces. And here again, this, during failure analysis, if you are seeing this kind of a fracture surface, then it is quite possible that failure has happened due to impact. So the HOD, Dr. Binu Eldos, he touched upon failure of Titanic ship. As you know, the Titanic ship began its first voyage from England to US on the East Coast in New York. That was in the year 1912. And 2 days after it started its voyage, the ship struck. See, at that time, it was the golden standard for this Titanic was the golden standard for luxury liners. However, 2 days after it started the journey, it struck a huge iceberg. Size was considered to be some 3 to 6 times the size of the ship itself. And when it collided with this huge iceberg, it damaged the hull and several forward compartments were broken. Water entered and the flooding in the compartment was enough to cause the ship to sink in a matter of few hours, and close to 1,500 lives were lost. So this is a lot of failure analysis has happened on this, and of course one can read all the literature. But the sum and substance is that the failure of the hull steel resulted from brittle fracture. And why did it fracture in a brittle manner? Because the steel contained very high amount of sulfur. We all know that sulfur is not good for ductility. And this particular shipping steel, it contained a lot of sulfur. So it had very poor ductility. Secondly, the temperature of the water was very low, close to 0 degrees centigrade. And thirdly, it's a huge, very powerful ship. So it went and hit the boulder at a very high speed. So the high impact loading also added to the reason for fracture. So when Titanic hit the iceberg, the hull plates simply split open and the crack propagated and the ship sank. So people taken the parts and studied the impact properties. What you see here is the impact curve of the material taken, the material from that Titanic ship. You see this curve. Normally, in impact test you do in 2 directions. 2 directions means you look at the rolling direction of the material, and always the longitudinal direction will have higher toughness than transverse direction. So usually impact tests are done in both the directions. So you see here, this is the impact curve, the impact energy curve for this particular Titanic ship material, the longitudinal one and the transverse one. And you see that the absorbed energy is almost 0 at 0 degrees centigrade. Okay. So it's almost having 0 toughness. Whereas today's, ship steels will have very high impact energy. You see the upper shelf energy value even at minus 25 degrees centigrade, you have more than 300 joules. Whereas the Titanic ship had almost 0 joules at that temperature. And these are some of the fractographs out of the failure analysis studies on the Titanic ship failure. You can see very clear evidence of impact failure. Now creep is yet another important, Dr. Ishwar Prasad, he mentioned about creep, because creep is not so common unlike tensile or impact studies, because creep is a little bit more complex and it is very expensive also. So creep represents the behavior of a material under constant loading. In tensile, you are continuously loading. In impact, you are continuously loading. In fatigue, you are cyclically loading. Of course, you increase the load and then you, of course, reverse it. Whereas in creep, the load is kept constant. Still, the material will deform, damage, and fracture after a certain amount of time. And that depends upon the temperature and the time. So creep is defined as the slow and time dependent deformation of a material which occurs at high temperature. Because at high temperatures, permanent deformation can occur at stresses which are smaller than the yield stress. Okay. So depending upon the magnitude of the stress and the time duration, which normally runs into years and years, the deformation can become so large that the material will undergo failure. So the factors or the variables that govern creep are temperature. It has to be greater than 0.4 times the absolute melting point of the material. The time has to be very long and the load can be constant. When you talk about creep, or like you talk about tensile curve or an impact curve, here you have the creep curve. This is a curve between time and strain, because in this case the load is constant, temperature is constant. The only variable is time, and when the time changes, the strain increases. So this is a plot of strain as a function of time. And there are three stages in this curve, primarily a primary region, a secondary or steady state region, and a third region called tertiary region. And the end of that tertiary region manifests the rupture of the material. And every test, how much time it has taken to fracture is called the rupture time. So one can always, do several tests, each test at one particular stress, and so many tests at so many different stress levels. But
Dr. Mathew.
So, you, as I said, at one temperature, you carry out, so many tests, each test at one particular stress, determine the rupture time, and then you make a logarithmic plot, time to rupture on the y-axis and the stress, and you get one rupture curve. Like that, you can determine, you can keep on doing tests at various temperatures, and this is what is normally the kind of data that one gets in a creep test. But what I'm coming to is about the creep damage. What is the creep damage? Creep damage is mostly in the form of cavities. How do cavities form in creep? At those high temperatures where creep occurs, grain boundaries start sliding. The strength of the grain boundary is lower than that of the grain interior. At room temperature, low temperature, grain boundary is stronger than the grain interior. But at that temperature called equicohesive temperature, the strength of the boundary is less than the strength of the grain interior. So under the action of a shear stress, grain boundaries start sliding. So when this boundary slides and this boundary slides, then it leads to a certain amount of stress concentration at the point where the three grains meet. That is called the triple point. So under the action of this stress concentration, cavity starts developing. Okay. And then, vacancies start flowing into it. You are talking a high temperature, so the concentration of vacancy is large, so vacancy will flow into it. And as a result of that, the cavity will start growing. Another mechanism by which cavities can form by sliding grain boundary is when you have a particle on the grain boundary. Again, when you have a particle, that the sliding is obstructed, and then there is a you develop a stress concentration, and then that leads to formation of a cavity. A third situation is where you have the slip bands. Deformation is happening, dislocations are moving on slip planes, and when such a slip plane interacts with a grain boundary, again it causes some stress concentration. And when so many dislocations and so many micro slip bands, they interact with the grain boundary, again sufficient stress is created, and a void is forming, a creep void gets nucleated. So this shows like examples from creep tested sample where you can see voids on the grain boundary. Okay, these are all creep voids which are seen on the grain boundary, and these voids will link together, and then they will form small cracks. The voids will join together and form small cracks. This is the case of some other material. This is what you saw here is an austenitic stainless steel. What you see here is a ferritic martensitic steel. Again, you see large number of creep voids. This is a magnified view. These are all creep voids, and then they will start growing, linking, and then it leads to a macro crack. Again, while most of the creep voids are formed inside the material, okay, creep cracks can also form at the surface. The surface gets oxidized. Creep is a high temperature property. Creep test is done at high temperature, so material gets oxidized on the outer surface. Oxidation can always initiate cracks. So tensile deformation is the damage forms inside, whereas in the case of creep, the damage can form inside as well as on the surface. This is another picture where you have a lot of micro cracks, internal cracks, and the difference between the top, this figure and this figure is on the amount of ductility. See, you see here the grains are very elongated, whereas you can't see that amount of deformation in this grain. So this is more ductile case, and this is a less ductile case. When it is a more ductile case, the crack itself gets elongated. Now this one represents the fracture surface in a scanning electron microscope for this kind of a damage in the material. You can see it's a case of pure intergranular fracture. The sample has separated along the grain boundaries. Whereas in the bottom one, where there has been a substantial creep strain, you get a mixed mode. A lot of signatures of ductile dimples are there. So if you see during a failure analysis investigation, if you see this kind of cracks and cavities and also this kind of fracture surface, then you can be pretty sure that yes, there has been a case of creep. Back to design, again the ASME code, it specifies that if you take a creep curve and you determine the rupture life, then you take 67% of the stress to cause fracture, or you take 80% of the stress to cause onset of tertiary, that is the stress at which the tertiary will start, or full 100% of the stress to give 1% of the creep strain. So 3 stress values are taken. Either you take the rupture stress and take 2/3 of that, or 80% of the stress to cause tertiary, or 1% of strain. What is the stress that causes 1% strain for a given 1,000 hour, 10,000 hour, 100,000 hour, whatever it is. And the lowest value of that is considered to be the allowable stress for can be used in creep. Now let me come quickly to fatigue. Fatigue is a case where a material is subjected to cyclic loading. Okay, and when the material is subjected to cyclic loading, that is repetitive loading, it will fail after a certain number of cycles depending upon the stress range. Okay, and then the cyclic can be within the elastic limit. That means the load that you are applying, the cyclic loading is below the yield stress. So that represents the high cycle fatigue. Or it can be in the plastic region. You are deforming the material between tensile and compressive modes, and the strain corresponds to the plastic strain. Then you get low cycle fatigue. Or you can introduce some hold, that is a creep component during cyclic. You cycle for some numbers, then you keep the load constant at the peak stress. And again, cyclic can be symmetric, like in this case, that is the stress amplitude in tension and stress amplitude in compression are equal. That is symmetric loading. Or it can be asymmetric loading, where this cannot be, it can start going like this. So the fatigue cycles can be divided into low cycle fatigue and high cycle fatigue. High cycle fatigue, you are cycling in the elastic region. In the low cycle fatigue, you are cycling in the plastic region. And another ballpark figure or a thumb rule is that when the number of cycles to failure is below 10,000, you call it low cycle fatigue. And when it is above 10,000 cycles, it is called high cycle fatigue. And when you do test at high cycle in the high cycle fatigue range, very often you will end up with an endurance limit. And mind you, the low cycle fatigue is always controlled by the ductility of the material, and high cycle fatigue is controlled by the strength of the material. And low cycle fatigue is important for power plant components, okay, like for example the steam generator, turbines, or aircraft turbines, engines. For all those kinds of components, low cycle fatigue. So the number of cycles to failure is less, but there's a lot of stress generated, mostly of thermal origin, thermal cycling. For example, startup and shutdown, or a change in the power. All those things can lead to thermal stress, and this thermal stress can correspond to large amount of strain. So it's a strain controlled deformation. So this is how it looks like you are cycling between two strains, plus epsilon and minus epsilon. So this is a strain waveform. And if you measure the equivalent load, then this is the load waveform. You are now from zero stress, you have gone yield stress, past yield stress, and you have entered the plastic range, and you keep repeating. And for every cycle, you will get what is called the hysteresis loop. For every fatigue cycle, you will get the hysteresis loop. So when you start, if you take a sample, start a fatigue test, low cycle fatigue test. So, and then you have defined, yes, I am going to cycle it between plus 0.6 and minus 0.6% strain. And this 0.6 is much beyond the yield stress. Yield stress is normally 0.2%. So 0.6 is well into the plastic region. So the moment I start cycling, at the first cycle itself, you find that the stress is equal to something like, in this case, 140 megapascal. But for the next cycle, and this stress is taken from this point, there is a maximum stress in each hysteresis loop. So you find that as you increase the number of cycles, the tensile stress amplitude, that is this one, the tensile stress amplitude, that keeps on increasing. It reaches a peak and thereafter it comes down. So this is what is called the stress response curve. That is how the stress responds to the cycles, fatigue cycle, and this will represent the failure number of cycle. So one can always, you will find that depending upon the strain rate, this response or the behavior of the material is different. And this is what is called hardening, cyclic hardening. So to move into the second cycle, in order to impose the same percentage strain, you have to raise the stress. When you go to the third cycle, you have to still raise the stress. So material is getting hardened and hardened. So it is called cyclic hardening. Now there are other materials where reverse is the case. You will have the maximum stress in the first cycle, and thereafter with increasing number of cycles, the stress keeps coming down and material fails. So this is a case of cyclic softening. So this is the shape of cyclic hardening, and this is the shape of cyclic softening. And cyclic softening happens because the material is initially in a very hard state, very work hardened, lot of dislocations. And as you start the cyclic loading, the dislocations get rearranged, they become, and then as a result of that, the resistance to deformation comes down. Whereas in this case, work hardening is happening. And normally in a fatigue load test, what you do is you do a number of tests and for different strain amplitudes and make a plot of strain amplitude versus cycles to failure. And on a log-log plot, this will be a linear curve, and it is normally called the Coffin-Manson plot. It's a plot between the plastic strain and the number of cycles to failure. And fatigue crack always starts on the surface. Unlike, tensile, which starts inside, creep mostly inside, also outside. Fatigue crack always starts inside and then it propagates through various stages. And the nucleation can happen at stress risers, or even the very plastic deformation, the slip process will generate what are called intrusions and extrusions. As the dislocations move along slip planes and come out at the surface, it will create what are called intrusions and extrusions, and they will serve as site for a nucleation of a crack. Once crack nucleates, in subsequent cycles, it will start growing, and then finally it will reach a unstable. So this is a schematic way of representing the crack, and always it starts inside the grain. Fatigue crack always is, most cases is transgranular nucleation, and mostly it goes through the grain. Sometimes it changes the path to intergranular mode. So if you have a fatigue failed sample, then you will find, and if you do a low magnification metallography, you can see where it has started and then how it has been propagating and what is the final phase. So when you look at a little bit higher magnification, it is very clear that nucleation has started here and then it has propagated outwards. So if you go to still higher magnification, you will see this kind of striations or beach marks. At a high magnification, you will find beach mark, and the separation between each mark is a function of the cycles to failure. So this is a typical fingerprint or a signature of fatigue failure. This is another example of beach mark on a fatigue failed sample. And again, coming to design, normally we apply a factor of 2 on strain or a factor of 20 on life. That means if I do an experiment in the laboratory at say 1% strain and find out that 1000 is the number of cycles to failure, when it comes to design, I will take 1000 divided by 20, that is 50 as the number of cycles to failure. Now in human history, one of the most, the worst technological disaster has been one of the engineering failures associated with the explosion of the space shuttle Columbia. Okay, the US, the NASA had a very vigorous space shuttle program, and it was a reusable low Earth orbital spacecraft. Okay, and they had a fleet of 5 shuttles, 5 spacecrafts, and 135 launches, and then it started in the year 1981 and it was stopped in the year 2011. These 5 space shuttles were Columbia, Challenger, Discovery, Atlantis, and Endeavour. And most of their work was related to the International Space Station. So when NASA launched, the Columbia, its 28th mission, Columbia's 28th mission on January 16, 2003. And on February 1, 2003, as it descended back to Earth after completing a 16-day scientific mission, Columbia broke apart over the northeastern part of the Texas state in the US. And all the 7 astronauts aboard were killed. Okay. So one of the history's biggest failure analysis study was carried out to find out what caused the Columbia accident. Okay. And it turned out that the physical cause was the damage to Columbia's left wing by a 1.7 pound piece of insulating foam. That insulating foam got detached, okay, seconds after launch. And not only that it got detached, that foam strike created a hole on a reinforced carbon-carbon panel on the leading edge of the wing. And that allowed superheated air at a temperature of something like 3000 degrees centigrade to enter the wing while the shuttle was coming back and entering the Earth's atmosphere. So the extreme heat that caused the wing to fail structurally created an aerodynamic force, and it led to the disintegration of the space shuttle. So I will just want to show you a short video of this failure analysis study. Are you able to see the video? Are you able to see?
Yes, sir.
Okay, let me stop that video there because I overshot the time. So I only just wanted to, highlight the importance of failure analysis and some of the major causes. So, am I audible? Am I audible?
Yes, sir.
Okay, so I think I will now come to the end of my talk, where I touched upon various kinds of deformation and how it causes damage and how these damages can cause failure. So thank you very much for your attention. Thank you. Sorry for taking a few extra minutes.